Hello, my name is Hiche, and I'm group leader of the Theoretical Materials Chemistry group in University of Cologne, Department of Chemistry. Today I'm going to talk about how to accurately predict photochemical reaction activities on semiconductor surfaces using DFT calculations. Because I prepared for this material and talk because so far, the DFT calculation analysis on photochemical reactions on semiconductor materials have not been very successful due to discrepancy between real materials physics and the DFT calculation situation. So I corrected my the theory model a little bit myself with my group members, and I'm going to talk about how to do it. Okay. I prepared for this the cover image because the most common examples of photochemistry around us is photosynthesis. Yeah, with the light energy and water, the plants produce the sugar with the CO2. So with the light energy, electron and hole carriers are generated, and those carriers are used to convert the CO2 to sugars. So this is very common and well-known example of a photochemical reaction. So I'm going to talk about photochemical reactions and adsorption energy, correction for semiconductor, and activity predictions for photochemical reactions. So, and I'm going to present two examples that I have recently explained experimental phenomena very successfully with my corrected new theory model. And the first one is P-type cerium oxide, which is good for methane decomposition. And the second example is why reduced anti-TiO2 is good for water splitting. So this, as the first time, I explained the why defect chemistry and why and how defect chemistry can change the water splitting activity by photochemical reaction. Yes, the most common photochemical reactions in energy conversion is photocatalysis and photoelectrochemical reaction. The photocatalysis is literally with photon energy, it produces hole and electron, and those are used for oxidation and reduction, and sometimes TiO2 photocatalyst is used for organic decomposition, and it is mostly used for water splitting and hydrogen energy production application. And PEC, photoelectrochemical reactions, are also very useful for water splitting. This is the combination of light energy and bias, and it which much accelerate the production of H2 hydrogen energy. So, why? I tried to break down the photochemical reaction into three components. The first one is optical transition. First, when light energy is instant on the semiconductor material, then optical transition should occur first, and then hole and electron carriers are generated. For optical transition, we have to consider orbital overlap between the ground state and excited state. So the overlap of the orbiter function determines the probability of the optical transition. This is well summarized in Fermi golden rule and selection rule. So this is well understood and well known. The second thing is charge carrier transport. After optical transition, when electron and hole carriers are generated, the charge carriers should transport very efficiently in order to make a very high catalytic activity. The third part is catalytic reaction activity. This is for metallic materials. The catalytic reaction and the relation between catalytic reaction activity and adsorption energies are very well understood and very clearly explained with the DFT calculations. But for semiconductor materials, this part is not very successful to explain the experimental phenomena using DFT calculation by using simple DFT calculations. So that is why I started this work. Okay, let me compare the metal and semiconductor materials. For metallic materials, the adsorption energy of the anion on metal surface is always constant, almost constant, regardless it has low coverage or high coverage. But the problem is that on the semiconductor surface, let me say the Fermi level is around the center of the band gap, and then with the adsorptions of the charge donor, and then the Fermi level is shifted upward because the charge donor gives electron to the semiconductor system by adsorption, and then due to the increased electron carrier concentration, the Fermi level goes up. So, and then the electron transfer between the adsorbate and semiconductor substrate is determined by energy level difference between the Fermi level and the donor level, and the adsorption energy can be changed with the coverage change. And when charge acceptor is adsorbed on the surface of a semiconductor, then charge acceptor takes electron from semiconductor surface, and then the Fermi level goes down. Then adsorption energy becomes much higher, and which means that adsorption gets weaker and weaker with increased coverage. So we have to consider this, but nobody has considered this situation ever before. In general, DFT calculations predict catalytic activity only for metallic systems using adsorption energy. So DFT calculation for adsorption energy can be simply done by comparing the system total energy between the clean substrate system and substrate system with adsorbate. As you can see in the equation below, you can even for change of the bias and pH, you can get the adsorption energy that's this way. So please look at the upper slab, and you can predict the many catalytic reaction activity only for metallic system. For example, HER, as you can see on the left side and in the middle, that is the water splitting reaction activity. And the third one is nitrogen reduction activity. So you can do this very easily, only for metallic system. For semiconductor, this is the problem. In real nature, when acceptor adsorbate gets electron, then the lumen level is filled as the electron is given by semiconductor. And donor level of the adsorbate gives electron to the semiconductor. Then Fermi level, the electron is given to the Fermi level. Then this is how adsorption happens with charge acceptor and charge donor. But in DFT calculations, it has some limitation because when you get the Fermi energy, Fermi level, then the electron chemical potential is given to only to a VBM, which means that energy cost is much higher for adsorption of the charge acceptor because the electron is given from VBM, not from somewhere around the band gap center. Just if the Fermi level is around the band gap center, then it is much easier to give electron from a semiconductor surface to acceptor. And for the case of the adsorption of a donor, in DFT calculations, the donor's HOMO level gives electron to the CBM of the semiconductor. So this is the discrepancy between the real nature and DFT calculation. So we have to make new theoretical scheme in order to correct this, right? So what I did is first a Fermi level dependency of the adsorption energy and coverage dependency of adsorption energy. So Fermi level, this is how I corrected the adsorption energy for a semiconductor system. When people mostly do DFT calculation of the adsorption energy, the people just takes the three terms. This is very simple, but for semiconductor system, we assume that for charge acceptor or charge donor, we have to consider the charge state of the adsorbate. So this is the Q is the charge state of the adsorbate, and epsilon F is the Fermi level, and E VBM is the energy level of the valence band maximum. And we also corrected the potential energy for the charge of the slab. So for example, this is the CEO2 surface with the methane adsorption. We assume that this adsorbate can be charged Q, and this is how we correct it. We follow the very general correction method for charged slab. So the first example is a cerium oxide. This has band gap of 3.2 electron volt. The reason why I started this work is that when it is doped with a p-type dopant, its catalytic reaction activity becomes much better than the pristine material. So this is why we started this. So first, we calculate the adsorption energy of a CH4 as the reactant, and the second level with the decomposition after decomposition to CH3 and H, we got this adsorption energy, and we found that CH3 is only charged +1 according to the adsorption energy for different three different charge state. +1, -1, 0. So in most cases, people consider only charge state 0, but we found that the charge adsorbate should be considered when we calculate adsorption energy of the gas molecule on semiconductor surface. And the third state, it is sometimes neutral for low Fermi level value, like under 0.9 electron volt, it is neutral, but above 0.9 electron volt Fermi level, when Fermi level is higher than 0.9, then its charge state is -1. So interestingly, for example, when the Fermi level is at the center of the band gap, in the CH3 step, its charge state is +1, but in the next steps, when it becomes a CH2, it becomes a -1 with the Fermi level at the center of the band gap. And the next level it is also interesting that its charge state is changed from +1 to -1 with increased Fermi level to near to the conduction band. And when the C carbon, the last step is adsorbate, is always in charge state +1. So we calculated the adsorption energy difference. I mean the energy uphill for each step, and we got according to a rule of the least energy uphill step. We found that the best Fermi level for CH4 decomposition by CO2 is 1.29 electron volts. So and then with the Fermi level at 1.29 electron volts, then yeah, the energy landscape for its catalytic reaction step looks like this, and its energy uphill is 2.28 electron volt or 2.29 electron volt, and this is the best situation. Otherwise, if the when CO2 is in n-type state and its energy uphill becomes like a much higher value, 4 electron or 5 electron volt. So from this calculation, we could theoretically say that p-type dopants are beneficial for CH4 decomposition by CO2. So, and this is the examples of the experimental literature, which shows that p-type dopants makes a much better catalytic reaction of the CO2. So we can say that our theoretical analysis successfully explain why CO2 makes better catalytic reaction activity in molecule decomposition. And the second example is rutile TiO2. This was recently published by in collaboration with Professor Kim and Professor Park in SKKU and Yonsei University. And I started this theoretical analysis by observing very interesting thing. The first one is when we reduce the rutile TiO2 further, I mean, reduction means more oxygen vacancy on TiO2, and then TiO2 becomes much durable against the corrosion. When you can see in the figure, the corrosion of TiO2 occurs by a reaction between the H plus proton and the substrate, the Ti atom. And then, but when OH functional group is covered, when it covers the surface of a TiO2, the corrosion does not happen. So, and the more good thing is that the water splitting was accelerated, and it is also beneficial in pH independency. So as you can see in the graph at the bottom, OHRTiO2 means OH covered rutile TiO2, and the RTiO2 means just a normal rutile TiO2. So normal rutile TiO2 water splitting activity is largely changed with pH value. Acid means pH 0, and neutral means pH 7, base means pH 14. And with when it goes to acid condition, the water splitting activity becomes much worse. So, but with the OHRTiO2, I mean, when it is reduced, it is almost the pH independent. So, why reduction makes the water splitting performance less pH dependent? So, I started my theoretical analysis in order to answer those two questions. When oxygen vacancy is increased, then the free electron carrier concentration is increased in order to keep the charge neutrality, and then Fermi level is upshifted, right? So and then water splitting activity was much improved, as you can see in the figure at the center. OHRTiO2 has a much larger current density with the potential compared to RTiO2, and charge transfer efficiency is also improved. Charge transfer efficiency means that larger charge transfer efficiency means that OHRTiO2 has a larger band bending near surface. In order to have a large band bending on near surface, then it has to have much higher than negative surface charge. So let me say that it is on TiO2 surface. As you can see here, the OH minus competes with H plus on adsorption site. So they compete. So when OH minus is dominant in coverage, then the surface charge becomes negative. But when H plus is dominant over OH minus adsorption, then the surface charge becomes positive, which is not good for water splitting. So as I told you in the last slide, with the OH coverage, water splitting becomes better, and it is pH independence. So I used the same method for Fermi level variation. We considered the charge to adsorbate and correction. And for pH variation in water, we modified the model for aqueous H plus ion adsorption. We just use the very normal reaction constant equation, and because it is a function of the activity of a certain ion or certain species, we converted the H plus concentration into that in that way, and we this is how we obtained the coverage as the function of pH. So using these equations, we obtain the adsorption energies of OH minus, H plus, and H neutral H on TiO2 surface. Yeah, we with the three different pH value 0, 7, 14, we obtain the adsorption energy. And the arrow in the graph means the shift of the Fermi level. And for lower Fermi level, the OH adsorption energy is higher, so which means that adsorption is weaker. But with the shifted Fermi level, because the OH minus adsorption energy has a slope of -1 with a Fermi level, then the adsorption becomes much stronger. In this graph, negative value means stronger adsorption, and positive adsorption energy means a weak adsorption energy. Because we expressed the adsorption energy of an ion as the function of Fermi level, we could successfully explain how the coverage adsorption is changed with the Fermi level shift. So, and net surface charge is the difference between the H plus coverage and OH minus coverage. So we could obtain net surface charge this way. And please look at the left side figure. And I told you that in low pH, the OH RTiO2 is less pH dependent. So this shows that the net surface charge of the OH RTiO2 is much smaller than normal TiO2. So this is how reduced the TiO2 has much less pH dependency. And surface OH minus coverage is much higher when TiO2 is reduced. Let me repeat that. OH RTiO2 means a reduced TiO2 because it has much larger OH coverage on surface. So our theoretical analysis could successfully explain and predict the surface charge and surface coverage of the charged adsorbate. So yeah, this is the conclusion. Photochemical reaction activities on semiconductor surfaces have not been successfully predicted or analyzed yet. So surface reaction activity could be well predicted or explained with our modified model. So because we considered adsorption energy on surface as the function of the Fermi level. And considering the potential difference between the bond level and redox level, photoexcitation effects can be also expressed in accurate reaction pathway prediction. Thank you for listening.